thank you everyone for joining. So my name is Chris Drexelius, and I am the product owner for storage and compression for Db2 with BLU acceleration.
And my name is John Hornibrook, and I work out of the IBM Toronto lab on areas related to query optimization and spatial analytics.
Good, thank you. So thanks everyone for joining today, and today we will be discussing what's new with Db2 BLU in version 11.5 and beyond. So not just what's here today, but what's coming soon. Okay, so we're going to cover quite a few topics today. So we're going to start off and discuss insert, update, and delete performance improvements. So these are very notable and important for this release and also beyond, as well as large objects, spatial support, temporal tables, triggers, RI, and indexing. Okay, so let's start off with insert, update, and delete performance. Right. So the key point here is, as you probably know, this area of performance as well as compression, which we'll talk about in a bit, these are critical for not only the space savings that Db2 supports, but also to achieve maximum query runtime performance. So the biggest thing that we're doing here in version 11.5 is expanding our core-friendly parallelism for SQL-based IUD operations. Right? So how are we doing that? So what we're really doing is we are leveraging some of the capabilities that are commonly used in our query runtime engine already to really maximize performance. So for example, we're going to use a technique called Kiwi, which is kill it with iron. In other words, we're able to make greater usage of the processors and CPUs and cores that are available, as well as maximizing the cache and cache line efficiency. Right, so the idea here is we want to maximize ETL and ELT batch performance, and right, so our business is data, right? That's really what we're targeting. So these are critical improvements in this area, right? So there are a lot of general improvements related to reduced logging and better encoding performance and things like this. But the primary focus, what we're going to talk about today, is on bulk operations. So let's see a little bit more about what that actually means. Right. So here are some examples of what we're calling bulk insert and update. So the first example here is very simple. Right. It's an insert select statement. So we're just inserting into one table and selecting from another. The second example is very important. Right. So this is something new in 11.5. So this deals with external table load. So the idea with external table load is basically you have a flat file. So in this case, it's a CSV file. That's not necessary. There are other supported file types. But what this allows you to do is to essentially create what appears to be, it's like a virtual table, and you're actually able to execute select statements or joins and filtering and things like this on that table. Right? So in this case, you can, once you create your external table, it's very easy to insert into another table and just select from that table. And the key thing is this provides an extreme performance benefit over a lot of our earlier techniques, such as import and ingest and even load, right? So this is much, much faster. All right, some other examples include, right, a basic update statement, so nothing fancy or special here. And lastly, a CTAS statement, so create table as select. Right. So again, right. So it's a combo of a create table statement as well as an insert select, essentially. All right. So the first thing we're going to talk about, which huge value, is really leveraging multi-parallelism. Right, so we already had parallel insert, and this is something that allows for better scalability for large SMPs, and it's also heavily used with, when you combine this with MPP, this is really huge value to our customers. Right, so in this example, right, in the picture here, so query runtime is on the left and the insert processing is on the right. So, or insert or update. So what this shows is that, right, query runtime is able to parallelize across 4 subagents. So 4 is just an example in this situation. So previously, right, it was we only used one subagent to do the inserting on the insert side. However, now the number of subagents match the parallelism we use on the query side, right? So this is huge value. And I should mention that the degree that we're using here is actually determined at the optimizer level based on a number of characteristics and statistics. All right, so the next thing I really want to highlight is vectorized insert and update. So these are brand new for 11.5, right? So the idea here is that in the runtime engine, we leverage vectors. So what does that mean? Basically, that means that, right, we have a bunch of column values, and they're actually arranged in columns, right? So we have a vector for column 1 and a vector for column 2, and so on and so forth. So instead of processing things like a row, like one tuplet at a time for one single row, instead it's much, much more efficient to process everything from a single column and then move on to the next column. So in this case, right, bulk insert and update are leveraging the capabilities essentially that are already heavily used by our runtime engine. So as I mentioned, here's a picture that illustrates this, right? So what would we have done before 11.5? So number one, we would have formed a row from our vectors that we have, and then we would have processed it. So one value at a time per column, right? So first column, second column, third column, all the way until we get through all the columns. Then we would do any index support we needed, and finally we would do synopsis handling, right? So this is super inefficient, especially because for columnar tables, one column is a single extent. So to do just this 5-column table for just this base table would require us to touch 5 different pages. So this is super inefficient. So what are we doing today, right? So huge value here is we're going to work on the actual columns themselves. So we're going to work all the way through column 1. And then also as we do that, we'll generate what we're going to put into the synopsis and just hold it in memory. And then column 2 and column 3 and so on and so forth. And then finally, next we'll do any index updates we need to do, right? We've already computed all of that information as we do the inserts into the columns. And then lastly, we'll do any synopsis processing, right? So based on what we have already computed in memory. Okay, next, so along these lines, to kind of pair that with vectorized insert, we've optimized our bulk insert code path. So previously, inserts were all the same. There was no difference between bulk or trickle, which anything that's not bulk is considered trickle. And really, bulk inserts, whatever that really means in this sense, is things that leverage vectorized insert and update. So those are bulk operations. Right, but here we're able to really make use of the cache and cache line efficiency with the vectors that we have. And then also we have more efficient encoding and better data page filling. So we know that there's a huge amount of values coming in, so we can actually buffer up incoming tuplets and know exactly when we're filling a page, instead of kind of writing out a page and then adding some more information until we have really filled our virtual page and then merging everything together. That's extremely expensive, and that's how we do page compression today. But with this, we know exactly, once only things are in memory, what's going to fit, and that's really awesome from a page compression savings point of view. Right, and then the index updates are also all batched together as we just talked about. Right, so these things together, and there's a little bit more that goes into this that we'll talk about compression in a minute, but what I really want everyone to take away from this is that with all of these improvements, right, we're able to get at least 5 terabytes an hour data ingest on the appliance, right? So, and that's minimum. So we're talking usually 5, 7, 10, right? These are the type of values that we're talking about in terms of performance, and this is a huge difference from before 11.5. So with this performance, this actually allows SQL insert to outperform our load utility, which used to be our best practice, by anywhere from 2 to 4 times or even more. Right. So this is now our strategic direction, and there's huge value here for customers. Okay, so now let's talk compression. Right. So BLU leverages extreme compression. Actually, I just mentioned the load utility, right? So that was previously the best practice. right? So now with these enhancements, the insert code path is actually able to outperform the load utility. Right, and we're going to talk also about the automatic reorg recompress, what that means in just a minute, right? But the idea with that is we're actually able to go through and recompress uncompressed tuplets. So also very valuable because, as I mentioned earlier, right, the higher rate of compression you have, the better your query performance, as well as, of course, your on-disk savings. Okay, so the basics of automatic dictionary creation. Right, so what we want to do here is build a high-quality evolved dictionary, build it fast, and right, we don't want to have a big impact performance-wise on inserts. That would be bad, right, because we want to maximize our throughput. So in order to get a better quality dictionary, one thing we're doing here is we're going to raise our ADC threshold. And all that really is it dictates the amount of data we sample before we build our dictionary, right? So the more data we look at, the better our dictionary will be because the dictionary is based on the actual values we're seeing. So in 11.5, now the ADC threshold is $500,000 or $500,000 rows for a single MLN and 1 million rows for multiple MLNs, right? But that's the total. So the per MLN threshold will, of course, be 1 million divided by the number of MLNs. Okay, so the way this, right, automatic dictionary creation, we're going to start the insert, collect the data we're seeing, and then build a dictionary. And then only after that dictionary is built, then everything is compressed. Right, so that's a generic model that we're going to use for ADC. Right, so previously all we had was asynchronous ADC. And what that means is that we execute a background transaction. And that transaction scans the data pages that the insert threads are writing and also the in-memory page that may be currently being built. Right, we're populating, right, we're working with the current page, so that's still in memory. So right, we build up histograms to find the frequency of all our values, and we also collect those across database partitions. And then finally, we build and distribute the evolved dictionary. All right, so let's talk about vectorized ADC, right? We want to focus here on bulk inserts, and this is really optimized for bulk insert. So this is our new gold standard for ADC. So it actually executes within the insert threads themselves, and actually even across streams. So what does that mean? That means that if you're inserting into an empty table and you're doing bulk inserts, if you have 8 streams running, right? So that could mean many insert threads because they're all parallelized with parallel insert we talked about earlier. But all of these threads across all of these streams work together and they contribute their vectors and they're able to work together to build that dictionary. Right? So you get an amazing dictionary really fast, and not only that, but then once the dictionary build starts, we actually delay our insert threads a little bit to complete the dictionary, and that allows us to have more compressed data and less uncompressed up at the beginning of the table. Right? So in the picture, if you look at this, right, we're going to process one column at a time again. We're going to really leverage those vectors, and then right, those are going into our histograms, and then we're going to build our dictionary, and once we reach our ADC threshold. So let's talk performance, right? So this is another huge performance impact item. So I really want to make clear the impact that this has. Right, so what's shown on this chart is some performance results for TPCH. Right, so we have a 100 gigabyte data set, and this is on a single node. And this is it's a sailfish, similar to a sailfish machine, only just a single node. Right, so on the insert performance side of things, we're getting easily, right, more than 3 times performance speed increase. And the compression ratio you can see on the right is gigantic. So effectively, we go from near 0 compression to, huge compression ratio. So you might be wondering yourself, how on earth did this happen? Right? This doesn't really make a ton of sense. So let me explain. Right? So what's happening here is previously, as I mentioned, we used our background process, the asynchronous ADC, to build the dictionary. So the way that works, as I mentioned, it's scanning the data pages you're writing as well as what you're building in memory. So effectively, it's kind of competing with the insert threads to look at what's being written and what has been written. So effectively, they're kind of fighting with each other. And you wouldn't think it's so dramatic, but actually that's a huge performance impact here. So as soon as you take away that contention, that's where this huge decrease in huge increase in insert performance is coming from. And as you can see, so we are able to build the dictionary super quickly and then insert pretty much everything compressed. Let me give you another example, just as a frame of reference. So for one of our customers, so on the appliance, so they tried out Vectorized ADC because they were having problems with insert performance and dictionary creation. And what they saw is, so with their data set that they were working with was one table, and this is of the appliance, remember. So the data set they have was 712 gigabytes. So when they inserted this, they even have the results for Db2Z. So it was about 162 gigabytes compressed on Db2Z. So when we inserted that before we had Vectorized ADC on LUW, it was also about 160 gigabytes. However, it took many hours to complete. So that was totally unacceptable for that customer, and so that was a serious pain point. So once they had Vectorized ADC, they repeated that insert. So instead of 160 gigabytes, now it was 55 gigabytes, and the insert completed in 25 minutes. So they were shocked. In fact, the folks who were trying this out, they contacted us and they said, your new feature must be broken. There's no possible way it's working properly. They couldn't believe what they were seeing. Okay, good. So that's right. So those are the features for bulk insert that are really working together. I mean, there's a little bit more we'll talk about in a second, but those are most of the features that are working together to provide huge value in 11.5. Another important note, though, is there is this other type of ADC called synchronous ADC. So this one plays a lesser role these days, but the idea is, there are these cases where either you have a very heavy lock on the table, like the Z-lock. So for instance, CTAS, NLI, and insert into uncommitted tables. So if you create a table but don't commit and start inserting, so these are cases where there's a huge lock on the table. And whenever we would try to previously use async ADC, async ADC can't get through that lock. So we were effectively able to get zero compression in all of these cases. So today in 11.5, any case in this list that does not work with the bulk inserts we just talked about, we'll still be able to use sync ADC, and we will be able to use we will be able to build a dictionary, and we will be able to get compression. So this is also very important. The other case here is DGTT tables, so declared global temps. So these are notable because, so previously we had async ADC only. So temporary tables are only accessible in the transaction that creates them. So this means that, so the background transaction, when ADC is running, it's not able to access these tables. So again, there's no dictionary built, so we get no compression at all. So now, again, here, with sync ADC, we are able to get compression for those tables as well. Okay, so let's discuss Auto-REORG Recompress. Another name you might have heard of this as is grooming. So we talked about ADC already. So the idea with ADC, as we already discussed, is the first portion of the table, the data is written uncompressed, and then once we evolve the dictionary and build it, the rest of the table will be compressed. So it's good that we're getting compression with ADC. However, there's this upfront portion of the table that's not compressed at all. So this has a huge impact on query performance, right? We already said that the query performance is directly tied onto the amount of data that's compressed. So you're going to take a hit if that yellow portion of the table is large. So how does this work? So the idea is once the insert transaction commits and completes, then a background process automatically, so there's no user action needed for any of this, comes along and recompresses all of those early rows that are in yellow, right, to be able to use that evolved dictionary. So now everything in your table is compressed. Okay, so let's talk a little bit about some enhancements that are going to be coming post v11.5, right? So please note that right, these will be available in some future mod pack for on-prem customers, and they'll also be rolling out to the appliance and the warehouse on the cloud, public and private. But they'll be rolling out there quicker, right? Most likely because they don't follow the normal mod pack release timelines. So what we're going to talk about here are actually three things. But number one, we're going to talk about trickle insert enhancements, right? So I said that most of our enhancements here are targeted at bulk insert. However, trickle insert is still very important. So we'll look at that in a second. And secondly, right, is the improved compression of string data types. So in v11.5 and earlier releases, truthfully, this was kind of one of our weaker spots. We don't have great compression for a lot of string data, and we'll talk through why that is and what we're doing to solve that problem. And the third thing I want to talk about is the usage of the reorg recompress function to be able to support dealing with fragmentation issues that can come up in BLU tables. So that's something else we're working on. Okay, so trickle insert. Right, what does that mean? So, in other words, it's anything that's not a bulk insert. So that might seem very vague, but it could be anything from insert values to a case such as used by data stage. Data stage breaks things up into smaller units of work. So it might be that. It might be something that's coming, right? So IDAA is very interested in Db2 BLU, and so it might be something that's coming through IDAA. So there are various use cases here that are very important, and these are especially important, right, as we're moving along on our journey towards HTAP, right? So that's something we're headed towards. So this is really starting to solve the problem of smaller insert, update, and delete. Right. So this is a key case for us. So we do want to tackle it. So, for example, as we talked about before, when you insert this row, let's say a single row, into a column or a table with 5 columns, right? So that will require, in the 11.5, that will require us to write data into 5 different pages. So from an OLTP transaction type workload, that's not going to be acceptable. We're not going to be able to meet our performance targets there. So how are we going to solve this? So basically, what we're going to do is, the idea here is primarily we want to get that data in as fast as we can. And it needs to be able to be interpreted, but then later on, at some point, we can actually transform it into our regular columnar format that's split up into 1 page per column. So in the beginning, what we're going to do is actually write those columns all into the same extent, into the same page even. Right, so this will be more like what we do on the row store side of our engine, right? But it's something in this format. It's not actually using row store, but we do need to be able to interpret it. So that's very important. So the query engine, you still have to be able to query this stuff. So right, it needs to be able to understand and execute on this. And it may be suboptimal performance, but the idea here is it's a very transient format. So you don't have a lot of data in this format. So either synchronously or asynchronously, we'll be transforming that into a regular columnar format. So there might be questions about exactly how that's going to happen and how do you know how much data you have and so on and so forth. Right? So what's important here is we want to, when we put things into the columnar format, we want to get to the point where we can leverage our vectorized and parallelized work, right? That's very, very important. So that's key. But beyond that, right, so this is still a work in progress, so there's still some things to be determined there. Okay, and next, right, so there's the improved compression of string data types. So what does this include? This includes char, varchar, graphic, var graphic, binary, var binary, and inline LOBs. So the thing here is, right, so we have frequency-based compression, but for things like URLs or geospatial data and some of this type of data, right, these values aren't really repeated, right? So when you think about frequency compression, our dictionaries are not able to really provide good coverage for the data set. And what ends up happening here, what we've seen from actual customers is that the string data ends up dominating the storage cost. And it's not even close. And in many cases, right, it just totally exceeds whatever we're able to handle on the entire box, which is completely unacceptable. So what we're doing here for this is actually adding another level of page compression that uses pattern-based compression, right? So it's a per-page compression, and with the patterns, we're able to shrink things down and then kind of add more to the page and keep shrinking things. And that allows us to maximize what's in the pages. So this is an actual customer example for financial data. So there's 17 billion rows. So we were basically able to shrink this data down, or this table down from somewhere around 6.5 terabytes down to or just under 2 terabytes. Right? So that was amazing compression we were able to get, and right, the customer was very pleased with this case. Okay. So last thing I want to talk about real quick is fragmentation. So what does that mean? So the idea behind fragmentation is as your workload, if it contains a lot of updates and deletes, right? Updates or deletes and inserts under the covers. So you end up with data that's kind of sparse across your table. So we do have reorg reclaim extents to be able to go back and reclaim extents. However, it's only able to reclaim extents that are completely empty, right? After everything's committed and everything has been deleted. So the problem with that is if you have even a single row left in an extent, you can't reclaim it, right? So that is something that is a big problem for a lot of customers. So what we're envisioning is, again, being able to find such sections of the table and be able to use our reorg recompress logic to be able to go back and essentially recompress things and kind of completely remove out those rows that have been deleted and be able to squeeze things down and then be able to still reclaim all the extents that are now going to be free after that process. Okay, and I think that's it for this part, so I'll let John take over now.
Would you like to do a switch of computers?
Sure. So
give that an attempt.
Yeah, so let's see. So I press this.
So we'll have a brief intermission while we try to switch laptops. And we're good. We're back on. Okay, thanks very much, Chris. Now for the next rest of the presentation, I'm going to talk about some of the other features that are coming in 11.5 and some that will be coming in some mod packs a little bit after 11.5. So the first one that is actually in 11.5 is large object support for column organized tables. So, it's pretty straightforward up until now. You have not been able to create a column organized table with the various log types, and now you can with all the ones that are supported. And the way it works, it's very similar to row organized tables. The blob metadata and any inlining will actually be stored on the column organized data page, and then the rest of the LOB data will be in the same storage space that's currently used for row organized tables. And one of the more important things with this support now in column organized tables is that the more and more of the query processing will occur down in the column organized engine, which will lead to overall better performance. And it's also good to have some of the inline data on the page because it will benefit from some of the encoding and compression techniques provided by BLU. The next item that's coming in 11.5 is something called Spatial Analytics. Now, this is very similar to the spatial extender support that has been in DB2 for many, many releases. The main capability here is that it's going to be supported for column organized tables, which is something that the current spatial extenders couldn't do. So the externals are very similar to what's there for spatial extenders, but there are a few small differences, mainly around the schema, and a few architectural differences in terms of how the spatial analytics is supported. But before we, get into the details on what's coming in 11.5, I'm just going to do a quick overview of the existing spatial extender support. So what DB2 provides in that area is it's some additional functions and geographic information that gets stored in the database. And these, what these spatial functions and data types do is allow special spatial data to be stored in the regular user tables. And so with geographic data, there's a variety of kind of types that can be used to represent things like points or lines or polygons or other complex shapes associated with spatial data. And along with that comes some specialized functions to allow you to do things to compute the distance between different shapes, or whether or not different spatial entities intersect. There's a whole rich set of functionality that comes with this support, and it works in all the form factors that DB2 currently supports. So single node, MPP, pure scale, and then because it's the common SQL engine, you'll find the capability in Warehouse on Cloud, and also in the IBM Information Analytics Server as well. So when you enable your database, your DB2 system with extender support, what you get are about 350 functions and methods that will appear in the DB2 GSE schema. And then there'll be some additional spatial metadata that gets stored in a separate set of tables, again in the DB2 GSE schema, that are basically like an additional set of catalogs for the spatial information. And the spatial types are based on DB2's kind of built-in support for abstract data types. So it is more of a strict kind of or explicit hierarchical geometry. So, for example, some of these types will have various attributes that are used to represent their different shapes, and these are all represented as structured types. And then the geometries themselves will actually be stored as blobs. And additionally, there is a special type of index that comes along with the support that works kind of in concert with the the existing DB2 row indexes. We call these index extensions, and this allows a more efficient way to query spatial data and perform kind of joins across spatial data in different tables. And the spatial extender is enabled and installed, so the libraries go into a different install path, and the administration of the the spatial data and metadata is done with the DB2 SE command line executable. So in 11.5, with the introduction of spatial analytics, going to get the same functionality as with the spatial extender. There'll be a few differences. Rather than using abstract data types, the various spatial shapes will be implemented using LOBs, and it'll be so there will be dedicated types that are created for all the spatial data, similar to what you got with the spatial extender. They'll have the same names, except they'll be created in the sysIBM schema. And there will be another set of tables that represent the catalog information for the spatial data, and again have similar content as with the spatial extender, and there'll be custom coordinate systems and that type of thing. And the SQL functions are based on the industry standard for SQL MM and OGC. You'll have the ability to construct and maintain and modify shapes and determine relations between shapes. So again, very similar features and interfaces for column and row organized tables. One difference is that they will be kind of installed on the system using the sysinstall object store procedure. That's also used for other things like the autonomic, the tables used for autonomic processing support and the explain facility, optimization profiles, those types of things. They'll also be used for installing the spatial analytics catalogs. So this next page shows some of, does a comparison between the existing spatial extender support and the new spatial analytics. And as you can see, they're very similar, except now the spatial analytics works for both column and row organized tables. And there's a difference in the spatial reference system. There's an explicit one now that's provided with the spatial analytics feature. So specifically, what do you get when you create these new data types? So you get the spatial data types. They're in the sysIBM schema. They have a kind of a soft hierarchy. They're not based on the built-in abstract data types. They'll be based directly on the blob data type. So the metadata representing the type will be stored as a prefix in the blob, and then the geometry data will be after it in the blob. So this is done because at this time abstract data types aren't supported for column organized tables, so these types are going to be just placed right on top of blobs. The catalogs, they're going to have similar schema to what you get with the Db2 GSC or the Db2 GSE ones, except they're going to be in the sysgeo schema. There will be a coordinate system table that'll be pre-populated with 5,000 different references, and a spatial reference system table with slightly less than 10 predefined entries. And this next page just quickly shows you the catalog views that are coming when you run the sysinstall objects. And along with that, there will be all the spatial functions, again similar to what you get with the spatial extenders, will be created in the sysproc schema. So in this case, the syntax is basically exactly the same except for the schema name. And then rather than using the Db2 SE command line to administer the spatial capability, this will be done through a set of stored procedures that will be implemented in the sysproc schema. And so on this page, we show the 5 different stored procedures that are going to be supported to do things like alter, create, and drop spatial reference systems, and then a couple to register and unregister spatial columns. And this next page, we show some examples on how you would use these within your database. So the first thing is to create some tables that have some spatial data types. So the first table is got some point data based on the SD point type, and then we've got another table, polys, that's based on polygon shapes, and both of them are column organized. So they have to be organized by column clause. And then you can, pre-populate them with insert, simple insert statements, and then use the full set of spatial analytic functions to query them. So in this case, get the area in fathoms for this particular spatial point or polygon. And this next page shows a few more examples of what you can do. Again, I think you'll find that it's all very similar to what's supported with spatial extenders today. The next feature I'm going to talk about is it's not in 11.5 immediately, but it's on the roadmap for 11.5 mod pack. And this will be full support for system-maintained temporal tables for BLU, so column organized support for temporal tables. So as of, just to recap, as of 11.1 mod 3, support was provided for user-maintained temporal tables for column organized tables. And what this means is that the temporal kind of syntax, temporal type of queries could be run against temporal data in a column organized table, but the actual maintenance of the temporal information had to be done by the user. So, for example, as if the a new version of the row had to be created or go into the history table, this would all have to be done kind of manually, through the application. So what a future mod pack will support is the full system maintenance of the temporal tables for column organized tables, and the support at that point should be effectively equivalent to what is there for row organized tables. Another feature coming is trigger and referential integrity support. This again is not in 11.5, but it's on the roadmap. We mentioned them here together because architecturally they're going to share a common infrastructure, which is the ability to flow data, from insert, update, and delete operations to query operations. So it's basically kind of like the idea of being able to, select from an insert, update, and delete, so that that newly, changed or deleted data can be checked to see whether, it should fire any triggers or check any referential integrity constraints or enforce any constraints, and so that infrastructure will be built to support that, and it will be good for both triggers and RI. And of course, the goal will be to provide similar performance to row organized tables, other than the existing differences for column organized, because of how updates are actually two-step operation requiring deletion of the old row and an insertion of the new row. And in terms of phasing, triggers will likely be available before RI, just because that is the what we're hearing from feedback from users in terms of priority. And finally, another feature on the roadmap is some extensions to the BLU index support that was introduced in mod 3. That had lifted most of the restrictions that existed when indexes were originally introduced in 10.5, but there are still a few that need to be lifted in order to get the support closer to what's there for row organized tables, and specifically the ability to use the BLU indexes for update and delete statements that reference more than one row. So that's a very high priority item that we'd like to get to. After that, the remaining items on this list, kind of in rough priority order, would be include columns, allowing concurrent, writers during a create index or reorg index, and at some point index advisor. And as we go down the list, the priority will probably be reevaluated as we get further into the 11.5 mod packs. At that point, that wraps up this session. It's J03, and Chris and I thank you for attending and learning more about what's available in 11.5 and the future.